Hi, thanks for the introduction. I'm Andrew from Adobe Research, and today I will be telling you about joint work with my friend Dillon, who was at Google for this work. Now, Dillon and I are friends for many reasons, but what truly bonds us is our shared love of fixed point arithmetic. And one day we were talking about fixed point math, as we often do, and we discovered that a fast approximation that we like to use for some very common filtering operations actually produces higher quality output than the thing we were approximating. So this is a free lunch. It's faster and higher quality at the same time. It's a simple idea, and the paper is short, but it's something that we felt everyone who pushes pixels for a living needs to know. But first, why do we care about fixed point arithmetic at all? So Dillon worked on Google's HDR Plus camera pipeline, and I work on Adobe Photoshop. And I imagine a lot of the GPU programmers here are used to everything being floating point, but in the land of photography, integers are king. Integer math uses less power, it has higher throughput on many processors, and in fact, some of the DSPs we use in photography don't support floating point at all. So when I say filtering, what I mean is taking weighted averages of integers. Why might we do that? Lots of reasons. If we want to reduce the size of an image by a factor of 2, maybe because we're constructing an image pyramid, then each output pixel might be the average of 4 input pixels. If we're bilinearly upsampling an image by a factor of 2, maybe in the same pyramid-based algorithm, we might use a 9331 filter, where each output pixel is that weighted average of the inputs. So at the top left output, the weight is largest on the top left input, lowest on the bottom right input, so those weights are 9 and 1 respectively. And at the top right output, the 9 goes to the top right input, and so on. And this 9331 filter rotates to produce each output, dividing by 16 each time to make it a weighted average instead of a weighted sum. Filtering is, of course, very common in 1D too, often because you're doing separable 2D filtering. Popular kernels are the rows of Pascal's triangle, perhaps because they're the binomial approximations to the Gaussian, but more likely because they sum to powers of 2, so the division is cheap. The even rows are commonly used for resampling, and the odd rows are often used for blurring. And if you think the odd rows are used for resampling, then we can fight after the talk. Now, in the integers, none of these weighted or averaging operations can be done exactly. With integer division, there's always some remainder you need to handle. So let's return to the first example and consider the math in the integers. We can't compute the exact average of 4 values. One option is to just round down, compute the floor of the average. This is obviously going to be darker than the true average because we threw away any remainder modulo 4. Well, let's quantify how much darker. If A, B, C, and D here are independent uniform random variables, then the discarded remainder after we divide by 4 has an equal chance of being 0, 1, 2, or 3. So the output will be, on average, 3/8 of an intensity level darker than the ideal output, what the floating point output would be. We also care about the peak absolute error, which is the maximum difference from the ideal answer. And the worst case for this average is when the remainder was 3, leading to a peak error of 3/4 of an intensity level. We can do better if we round to nearest instead of rounding down with ties rounding up, which can be expressed like this. You just add a +2 in the numerator. We still introduce a little bias because ties round up. This time the bias is positive 1/8. And the peak error is a little better, it's 1/2. That's as good as the peak error can possibly be, actually, because our output has to be an integer, and sometimes the correct output is exactly halfway in between 2 integers. But what we really care about is the bias, not the error, and I'll tell you why. Bias creates artifacts that make photos look worse. Here's a picture of a mountain scene, and we're going to zoom in on this crop in red. On the bottom left is that crop brightened a little, and it has something subtly wrong with it that's objectionable to the discerning pixel peeper. There are these purplish blobs in the chrominance channels on what is supposed to be gray granite. Now, Dillon traced these back to bias being introduced by filtering operations at high pyramid levels of a pyramid-based algorithm nested inside a long, complex camera pipeline. If we use unbiased filtering instead, the blobs are gone and the granite is gray again. So those blobs were produced with ties rounding up, which is by far the most common way people do things. Photoshop does filtering with ties rounding up. LibJPEG does filtering with ties rounding up. The video encoder and decoder you're using to watch this talk almost certainly does filtering with ties rounding up. In fact, it's so common that some instruction sets support it explicitly. And if you'll indulge me, I'll show you what the ARM instructions are for computing this quantity. Don't worry, I'm going to very slowly walk you through this. So first, we're using SIMD instructions because presumably we don't have a single instance of this problem. We're computing an entire image worth of output. So we should compute it using SIMD vectors. ARM's vector registers are 128 bits wide, which means they can hold 16 8-bit values each. So first, we'll load a vector worth of each input. So each of these instructions loads 16 8-bit values. Then we'll compute the sum of the first two inputs, A plus B. And this takes 2 instructions. That might seem like a trivial detail, but it's going to turn out to be the key reason that our technique is faster. So it takes 2 instructions because we need to widen to 16-bit integers so that the sum doesn't overflow. And 16-bit values uses 256 bits, which is 2 SIMD registers. And we need 1 instruction to compute each. So uaddl computes the first half of the output, and the imaginatively named uaddl2 computes the second half of the output. Then we use 2 more instructions to add the third input, 2 more to add the fourth, and then we do something called a rounding narrowing shift right, which adds 2, divides by 4, and converts back to 8-bit, all in a final pair of instructions. So the ARM instruction set is highly specialized for this computational idiom, as are many DSP instruction sets. Finally, we store the output. But there's another way to compute an average of 4 values, one that doesn't require 16-bit intermediates, which is going to immediately halve the number of instructions we need. We're going to construct it out of pairwise averages, because unlike a sum, an average of 2 8-bit values is still 8-bit. Averages can't overflow. So first I'll introduce some notation to keep ourselves sane. I'll say that up arrow applied as a function is the average of the 2 values. And down arrow, is the seal of the average of the 2 values, the average rounding up. And down arrow will be the floor of the average rounding down. So these instructions are rarely used, so you may not have heard of them, but most CPU and DSP instruction sets support each of these operations as a single instruction without requiring any wider intermediates. x86 weirdly is missing the rounding down variant, but you can emulate it pretty cheaply with some clever bit tricks. So we can compose these pairwise averaging operations to compute approximations of more interesting averages. So for an average of 4, we can compute the average of A and B, then the average of C and D, and then we can average those averages to get an approximate average of A, B, C, and D. If we round up on the first 2 averages, and we round down on the last average, then that neatly cancels out any bias. But this approximation throws away information at that intermediate step. We dropped a bit on the first 2 averages. So surely the peak error is going to be worse. How can we find out? Well, I can't easily figure out the peak error in this case on paper, but fortunately we have computers, and it's easy enough to just exhaustively check every possible set of inputs and measure the peak error. And when you do that, to our great surprise, we found that the peak error is as good as you can get. This is very strange. This is the point at which we thought we might be onto something. The assembly is just 3 arithmetic instructions for the 3 averaging operations. And that's the minimum number of instructions required to combine 4 inputs. So this is optimal in every sense. It's the fastest possible way to average 4 inputs, and it produces the best quality output according to our bias and error metrics. There's no trade-off here. Whenever you want to take an average of 4 integers, you should do this. So to recap, if you want to compute this average of 4 values, you should instead compute this, which we can represent as a tree of averaging operations, where the leaves are the inputs and the inner nodes are either average round up or average round down. Okay, let's generalize to different filters now. Let's say we want to compute a 1-to-1 filter instead, where we have A plus 2 times B plus C divided by 4. We can just take our previous tree and replace D with an extra copy of B. so that now B appears twice in the leaves, so it has double the weight. It's no longer obvious, to me at least, that this is unbiased because the two leaves are now correlated with each other. Also, there are multiple ways we could have done this. All that matters is that B appears twice at the leaves and A and C each appear once. So at first, the tree on the right actually looks like a better approach. We're averaging a value with itself, which means we can simplify it to this, which uses one fewer instruction. And in general, that is a good thing to do. However, in this specific case, if we exhaustively check bias and error, then we find that the tree on the left is optimal, but the one on the right is biased. So if you want to take a 1-2-1 filter, use the averaging tree on the left. And that brings us to the general algorithm for finding these trees, which I'll illustrate with a 9-3-3-1 filter, which, as you recall, is for bilinear upsampling. So first, we place each input at the leaves of a balanced binary tree a number of times proportional to its coefficient. So we have 9 copies of A, because the coefficient on A is 9, 3 copies of B, 3 copies of C, and a single lonely D. Then we'll just try all permutations of those leaves and all possible rounding directions for the inner nodes. Each of these is going to have a different bias and error, and we can just exhaustively compute bias and error of each until we find an optimal tree. This one rounds up everywhere, so unsurprisingly, there's a strong positive bias. So if we flip some rounding directions, things can get a little bit better, more tweaking of rounding directions. And finally, if we shuffle the inputs a little, we can find an optimal 9-3-3-1 tree. So this is just a big brute force search. There are a lot of symmetries you can exploit to make the search faster though. The big one is that averaging is commutative. So there often aren't that many meaningfully different permutations of the inputs. So now that we have our optimal tree, we can simplify it by collapsing any nodes that average a value with itself and checking for common sub-expressions. Now, there weren't any in this case, but when there are, this turns our tree into a directed graph. There are 6 inner nodes, so now this is a 6-instruction way to compute a perfect 9-3-3-1 filter. So compared to the standard way of doing a bilinear upsample, this is about 60% faster on ARM and x86, and it introduces no bias, so the output's a little better. So 2x upsampling is, with bilinear interpolation is very, very common. So we were very happy to make it 60% faster. We repeated this search for all the filters I mentioned at the beginning of the talk and a few more. And in every case, we were able to find an averaging tree that has 0 bias, minimum peak error, and uses fewer instructions on ARM and x86. So these are the measured speedups on ARM and x86 for applying these filters repeatedly to an array in CAD. They're just unconditionally faster, sometimes by a lot, especially on x86, where there are no widening add or rounding shift right instructions. We also have some evidence that this is a good thing to do from some real-world usage. The image I showed you earlier is from a real camera pipeline that has been used to take billions of photographs. This is the HDR+ pipeline used in Google Pixel phones. If you recall, bias at the high pyramid levels was causing purplish blobs on the gray granite. And on the right, Dillon replaced 59 separate filtering operations in the pipeline with our averaging trees, and the blobs are gone and the granite is gray. So this not only improved the quality of the output, but it also sped up the affected pipeline stages by 11%. So whenever you can use an averaging tree, you should. They're faster and better. Unfortunately, you can't always use an averaging tree. First, we've only shown optimal averaging trees for 290 different filters, including the ones in this talk. If you run our code for longer than we did, it will spit out more. And the list of filters along with pseudocode for each is in the supplemental material for our paper. We also have about 1,000 more trees in supplemental material that are unbiased, but don't have the minimum possible error. Second, the coefficients in the filter must sum to a power of 2. If you have filters that sum to other things and you need to divide by denominators that are not powers of 2, I know a whole separate family of tricks for that, and I'd be happy to talk to you about that offline. Finally, the coefficients of the filter must be positive, which rules out many useful filters that have negative lobes. But the overall message of our paper is very simple. If you're doing fixed point filtering and your filter is on our list, then use an averaging tree. It's faster and higher quality at the same time. And with that, I'd be happy to take questions.
Very cool. Thanks, Andrew. So this paper is related to the other two only in the sense that it uses a tree data structure at the theoretical level. But a lot of us here love integer math as well, being hardware people. So this fits right in. That's great. Let's see. Okay, here's our first question in the chat. And you can give your questions verbally with the step to the mic button or in the chat. The question is, have you considered similar techniques being useful for floating point operations and involved round-offs?
Not especially, no. I mean, in floating point, so I would say, first of all, another really common unbiased way to do fixed point filtering is with ties round to even. It has a few minor downsides. The main one is that it's more expensive. But in floating point math, I believe you can just set the rounding mode to ties round to even. And normally you have so much excess precision that that's perfectly adequate. So we haven't really considered these sorts of tricks for floating point for that reason.
Though if you're using an aggressively reduced precision floating point, like FP16 or FP8 or bfloat 16, this might become more important.
That's true. I have not thought about that.
Okay, next question. Okay, these are getting hard for me to read here. Let's see. Okay, it feels like there should be some mathematical property that can help design these trees directly without brute force search. For example, intuitively, I might expect average down plus average up, as in the motivating example might scale up. How hard did you search for such a mathematical property?
Yeah, so if you're combining two subtrees and they have completely disjoint inputs, then they're sort of mathematically independent. You know the final bits are uncorrelated, and you can compute closed form what the bias is going to be. But as you can see from the slide, we have directed graphs rather than trees with disjoint inputs. As soon as you have sort of overlapping sub-expressions being fed as inputs, it becomes sort of combinatorially hard to track what the bias is going to be. And it's really easy to just try every possible set of inputs. In a sense, look, this paper is much more of a discovery than an invention. We found that these trees exist. We don't know exactly why they exist.
But they're pretty darn cool. Okay, Jonathan, you want to ask your question?
Yes, great talk, great contribution. I was thinking about the geometry, well, the topology of these trees you've derived. So some of them are clearly symmetric. I'm looking at the slide right now. But so the rightmost one is asymmetric, but I would imagine that if you were to flip the configuration, it would be invariant, right? Would you get the same bias and error?
So you get the same bias and error.
Yeah.
The other thing you can do is flip all the rounding directions, and you get the same bias and error. It's also invariant to that.
Okay. Okay.
However, these filters are not always commutative. Actually, I have a backup slide that might be interesting. So we have a 1-1 filter, which is odd because it's an average of two values. And if you do ties round up, you get the thing on the left. If you do ties round to even, you get the thing in the middle. Something objectionable about that is the even valued outputs produce much wider bands than the odd valued outputs. And on the right, we have our averaging tree. And it's unbiased, and it's very fast, but it's not commutative, so that the transpose of this is not equal to it.
Yep.
So if you really care that two filter taps with the same coefficient, it should be invariant to permuting those, then you might need to add a layer on top of our averaging tree, or maybe not use an averaging tree. But for the applications that we're aware of, that property doesn't seem to matter.
Yeah, that's very interesting. Thank you.
Thank you. Okay, one last question in the chat. Lots of GPU hardware includes hardware texture units that perform filtering. Do you think this optimization might improve those hardware filters?
Yeah, at the hardware design level, quite possibly. We haven't, oddly for this conference, but we haven't really thought about GPUs, because on GPUs, the floating point units tend to be much higher sort of provisioned than the integer units. I know on much older, like the very first versions of CUDA had various packed fixed point operations that were sort of shuffled away. And if you try to use them now, then it emulates them instead. But I hadn't considered that you might actually want to design filtering hardware using trees of averaging operations. It's possibly true.
It's an interesting potential direction. All right, looks like we have one last question from Dillon. Go ahead.
I'm actually the co-author of this paper. I was just going to mention that another issue with using this for GPU hardware is that typically that hardware, like, you don't know that it's a 2x upsampling, for example, or like where the things are going to be sampled. Like, so this approach is used when you are doing like some kind of like fixed rate resampling, whereas the GPU resampler is kind of just very dynamic. They don't know that that's going to happen ahead of time. Maybe there's other parts of the GPU that do that, but I think just like the generic thing that I assumed we were talking about here, I think it'd be hard to do.
Right, yeah, because the topology changes as a function of the filter weights.
Good point. Okay, thanks a lot, guys. Andrew and Dillon. Okay, let's all thank our speakers one